All right, welcome to part 2 of 6.3, that's Pascal's triangle, and addressing the application of Pascal's triangle specifically for binomial expansion. Okay, because this is part 2, I am going to take for granted your knowledge of Pascal's triangle and how to identify any term of any row in Pascal's triangle, whether you're going to write it out or you are going to use a calculator as a shortcut. Either way works, okay? In this, though, I am going to use one of the shortcuts that I taught you, that I taught in the previous video, where if it's the n value is, let's say, the 6th row, and let's say the term number is the 4th term, so it's written as a 3, T6, 3, if you plug it into the calculator using the special number button combination MCR, it would be 6C3, or we can write it as 6-3. The reason I want to use this particular notation for today's lesson is because it's sort of nice and clean, okay, and concise. So if you're not quite sure, please go back to the previous video and take a look. It's not that difficult. I hope you'll be able to pick this up. If not, when I write 6-3, it means the 6th row, the 4th term. If I write 11-4, that would mean 11th row, the 5th term on that row. Okay? So if you're not going to look at the previous video and learn the shortcut for the calculator, then you at least need to know what this represents in your own understanding. Let's get started. Binomial expansion. So that we have a better reference, I am going to write out Pascal's triangle up to row 4. Maybe row 5 later on. Anyways, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and 1, 4, 6, 4, 1. What is binomial expansion? Well, let's break down the wording. Binomial would be, for example, this. It's simply a polynomial with 2 terms, binomial. Another example would be that. Another example could be that. As long as there are 2 terms in this polynomial, we can call it a binomial. Now, what is expansion? Well, expansion in the math lingo is just simply multiplying out, right? So if this was a 2, and I say expand, that would be you having to do the age-old FOIL, or distributive property, okay? If this was a 3, if this was a 4, whatever that case might be, you would have to multiply it out. So how is multiplying out a binomial to a power made easier by using Pascal's triangle? Here goes. As I write this pattern out, I would like you to not only sort of watch, but also see if you can make a connection between what I'm doing on this right side of the blank whiteboard and the Pascal's triangle I wrote on the left. Or if you want to just write it along with me, you might want to bust out a piece of paper. Let's take our first example, x plus y as my binomial. What is x plus y to the power of the row? Power of 0. Well, anything to the power of 0 is 1. Good. What is x plus y to the power of 1? Coincidentally, row 1. Well, nothing much changes. It would be a single x added to a single y. What is, though, x plus y squared? Well, let's do it here. Okay. If I have x plus y squared, it's essentially 2 brackets, the binomial x plus y multiplying itself. And if I use distributive property, I would get x squared plus xy plus xy plus y squared, which is essentially x squared I have 2 of the middle terms and y squared. Copying this answer, let me highlight that portion. Copying this answer into my little thing above, x plus y squared is 1x squared plus 2xy plus 1y squared. Do you see a resemblance between Pascal's triangle and when I expand a binomial? If that's the case, if you do see it, amazing. Take a guess of what my next terms might be. If you don't see it, I'm going to continue on. I'm going to expand x plus y to the power of 3. And that is x plus y, x plus y, x plus y. And that is, well, if I multiply the first two, that's going to be x squared plus 2xy plus y squared multiplied by x plus y. Because I am lacking space, I'm going to continue it here. If I multiply this trinomial with this binomial, I will get x cubed plus x squared y plus 2x squared y plus 2xy squared plus xy squared plus y cubed. Grouping like terms together, I have 3x squared y's. I have 3 xy squareds and 1 y cubed. I'm pretty sure I hear your jaws dropping all the way from where I'm sitting. Pascal's triangle essentially corresponds to, the rows in Pascal's triangle, if it corresponds with the exponent of the binomial, the terms in that row correspond to the coefficients in that row. 1, 3, 3, 1, 1, 3, 3, 1. I forgot to write that in, didn't I? Okay, let's use a different color. Let's try green. I have 1, 2, 1, 1, 2, 1. If I have 1 and 1, I would have 1 and 1, so on and so forth. So without actually writing out everything, let's use purple. If I have x plus y to the power of 4, without even doing it, I know that the first term is going to be a 1. Plus, I know that the second term is going to have a 4. I know the third term will be a 6. I know the fourth term will be a 4. And I know the fifth term will be a 1. And I know for sure that's going to have 5 terms, right? 5 separate terms. What is one way I can write it very concisely as a general equation? If I know what that's going to be, each coefficient from left to right, from I guess increasing to decreasing, it will correspond with the actual term number. So in this particular case, it would be nth row, the first term, plus nth row, the second term, plus the nth row, the third term, plus so on and so forth, all the way until I finally get to the nth term, the last, nth row, the last term in that row. Multiply by that. Okay. All right. But from here, your next question will be, all right, Pascal's triangle helps me to find the coefficient. What about the actual variables of each term? Is there a special way to calculate that? You guessed it, there is, okay? The simplest way, I'm gonna fill this final equation in, but I'd like you to, again, take a look at the pattern. Let me use a different color so you can really, really pop out. I will be using a brownish color. Please take a look at the first term. The first term is x. X has a power of 3. X has a power of 2. The x has a power of 1. And then the x, in this case, has a power of 0. 3, 2, 1, and 0. Does a 3 look familiar? Starting from the row number, the first term in the binomial will have the power that is the same as the row number and just go down by 1 every single time. 3, 2, 1, 0. In this case, it would be 4, 3, 2, 1, 0. In the top example, it would be 2, 1, 0. Here, 1, 0. You get the point. Okay? Think about it. So in this case, it would be whatever the first term is to the power of the row number. And then this one would be 1 less than that. And then this one would be 1 less than that. And so on and so forth until this would be x to the power of 0, which of course doesn't exist. What about the other term? Now I need a different color. How about I use hot pink? Take a look at the y value. The y value finishes with a power of 3. The term before it has a power of 2. The term before it has a power of 1. And the term before it has y to the power of 0. So long story short, the second term in the binomial starts with an exponent of a 0 and starts counting up. Or you can say the very last term starts with the row number and counts down. So in this particular case, this would be y to the power of 0. This is y to the power of 1. This is y to the power of 2. And this becomes y to the power of whatever my number actually is. Whatever number that is. Okay? Well, I guess of course you can also consider that to be r. I think data management actually uses the definition for r, so I'm going to write it like that. Okay? But the number is going to be the same. So this is binomial expansion. Okay? If you like, I'm going to erase the examples on the bottom. I'm going to try a couple of examples with you. If you don't want to waste time watching me erase this, please go to the timestamp and move on to the next example. My first example with you is going to be, let's do 2x plus y to the power of 4. Bam. I am going to give myself 5 spots. 1, plus 2, plus 3, plus 4, plus 5. Okay? Starting off, I know my coefficients are going to follow Pascal's triangle. That's going to be 4th row 0, 4th row 1, 4th row 2, 4th row 3, 4th row 4. I also know my first term is going to be 2x starts with 4. This is going to be 2x starts with 3. This is going to be 2x starts with 2. This will be 2x power of 1 and power of 0. For the sake of writing everything and getting used to it, I'm going to write it anyways, even though that turns into a 1. Next, my second term, the y is going to start with the power of 0. It's going to now power of 1, power of 2, power of 3, and power of 4. Simple as that. 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4, Pascal's triangle. Next, 2x, 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 counting down from 4. Y, counting up from 0. The rest is all calculator work. 4 combination 1 or 4 choose 1 is going to be 1. 2x to the power of 4 is 2, 4, 8, 16. X to the power of 4. And y to the power of 0 is just 1. Plus 4 choose 1 is 4. 2x to the power of 3 is 2, 4, 8. 8x cubed. And y to the power of 1 is just y. 4 choose 2. That's going to be a 6. 2x squared is going to be 4x squared. Y squared is going to be y squared. Plus 4 choose 3. It's going to be 4. 2x to the power of 1 is just 2x. And y to the power of 3 is going to be y cubed. And 4 choose 4 is going to be 1. 2x to the power of 0 is just 1. And so this is y to the power of 4. Simplify. 16x cubed to the power of 4. 4 times 8 is 32x cubed y. Plus 6 times 4, 24x squared y squared. 4 times 2, 8xy cubed. And y to the power of 4. Do you see the exponents? 4, 3, 2, 1, and nothing. And nothing, 1, 2, 3, 4. This is binomial expansion. Long story short, no matter what the exponent is, if it's a binomial, you can expand it without having to do any more distributive property. But this only works for binomials, of course. How about a harder example? If you want to try it on your own, you can do so, but I am going to try a different example with you. It's going to be a slightly harder one. And so my writing is going to be a little smaller. This is going to be x squared minus 1x to the power of 5. You ready? Okay. 5 choose 0. Actually, again, let's stick to the order. 5 choose 0. 5 choose 1. 5 choose 2. Sorry, plus 5, 3, plus 5, 4, plus 5, 5. Okay, remember, this is 5th row, 0th term. Okay, so the first term. Here we go. Next, x squared, x squared, x squared, x squared, x squared, x squared, 5, 4, 3, 2, 1, 0. Next, negative 1 over x. Remember, the negative is part of the second term. Don't think you have to leave the negative. Negative cut is a part of the term. That is a 0. That would be negative 1 over x to the power of 1. Negative 1 over x to the power of 2. It would be negative 1 over x to the power of 3. It would be negative 1 over x to the power of 4. And negative 1 over x to the power of 5. The rest is you simplifying. I am going to do a little bit of mental math. You can pause the video now and work this out and see if you get the final answer. But for me, it's going to be 1 x to the power of 10. Let's see, that's a 5. X to the power of 8, negative 1 over x, plus, that's a 10. That would be x to the power of 6, negative, or positive 1 over x to the power of 2, plus 10, x to the power of 6, negative 1 over x to the power of 3, plus 5, x squared, positive 1 over x to the power of 4, and 1, negative 1 over x to the power of 5. Simplified, this is x to the power of 10 plus, nope, minus 5x power of 7 plus 10 x to the power of 4 minus 10 x to the power of 3 plus 5 divided by x squared minus 1 over x to the power of 5. There it is. It's a bit long. And yes, when you have a negative as a second term of a binomial, it does make things a little bit weird. See the signs? It's alternating between negative and positive. But if you work it out and you're all right with your algebra and your exponents, it won't hinder you for long. This is binomial expansion by applying Pascal's triangle. Hope this is all right. If you have any questions, please, by all means, email me, ask me questions, do whatever you need to do. Your assignment, or rather your homework, is going to be page 378, 5 to 8. A bonus or, a challenge would be 15, 17, and 19. That's page 378, numbers 5 to 8. And as a bonus, try 15, 17, and 19. Okay, try it out. Please note, you also have a problem set to do, and that is going to be due the Tuesday before we have our next lesson. I believe that is going to be Tuesday the 21st. Please get that in, submit it to me. It will be worth marks, and it is going to be inputted into whatever evaluation, whatever progress report we'll get at the end of the year. All right, work hard. I know you're doing your best. Keep at it, and hopefully we'll see you soon.